Welcome back to our continuing study of Newton's laws, circular motion. In the previous lesson, we mentioned briefly the special case of banked curves. We want to look at those a little more closely today. On the screen, you see an example of a car moving in a banked curve. This is typical of the tracks you find in NASCAR racing. Okay, in Formula One racing, the tracks are flat, but in NASCAR, they are banked. Okay, and as we mentioned before, they give the car the additional advantage of having the normal force help push the car toward the center of the circle, which, remember, to move in a circle, you need a force on you toward the center of the circle. What's interesting about banked curves is the way that friction's behavior changes based on the speed of the car. So I want you to look at the two scenarios on the screen. On the left, we have the example of the car's basically, like, imagine the car's just parked on the track. Okay, so let's look at the free body diagram for that scenario. When it's just parked on the track, right, you've got your weight down like this, okay, and then you have your normal force perpendicular to the surface, like so. And then think about which way friction's acting here, right? Doesn't the car naturally want to slide down the track, right, if it's just still? Okay, so that means that in this scenario, friction's acting up the track, okay, so that our labels look something like this, okay? Now, let's move to the right. Let's look at this example here. This is when the car is moving at a very high speed. Okay. If we go back to the top, think about what happens when the car skids out. Right, it goes too fast for the conditions under which it's traveling. Okay. Hopefully, you'll see that. Let me use this track at the top. That it's going to actually kind of slide out like that in a straight line. Let me show you a picture of a racetrack. This is not a banked curve, but a Formula One track. Okay. And you see here, you see these skid lines. Okay, let me draw a few, right there. Okay, those are all straight lines, right, where the car basically moves to the outside of the track, right? So going back to this scenario here, interestingly enough, if this car is moving as fast as it can move, right, in other words, it's about to slide out, this free body diagram actually changes. Even though the drawing looks no different, actually friction is going to be changing its behavior. So we still have this right here, okay, a normal force and weight. But now since the car is, right, the outside of the track is this way, right? So friction is going to oppose that. So in this situation, when the car is like pushing on the edge of its performance limits, right, you're actually going to have friction acting downward like that, okay? So it's tricky, right, because you've got to know a little bit about the motion of the car before you can draw the correct free body diagram. Okay, so if the car is moving slowly, right, or not at all, friction is going to be acting up the ramp to keep the car from sliding down the ramp. And then if it's moving very fast, friction actually is going to be acting down the ramp. So let's see how those free body diagrams guide our equation writing. Let's take a look at the next screen here. All right, so we're going to look at these same two scenarios again, but we want to now write the F equals ma equation for the car in each scenario. A note on coordinate systems first, okay? Now you might look, when we take this snapshot here, you might think, oh, I should rotate my coordinate system because this is basically like an object on a ramp, okay? But remember, the guiding principle when setting up your coordinate system is that you would like to set up your coordinate system such that one of the axes, right, x or y, is in the direction of motion. And if you think about the direction of motion here, right, the car actually stays level, right? It actually stays level. So in other words, it stays like in this line here. It doesn't actually slide down the ramp, right? When it's moving around the track, it actually keeps the same vertical position. So believe it or not, even though this looks like an object on a ramp problem, we're actually going to maintain our coordinate axes as straight, horizontal, and vertical. So we're going to actually go like this, okay? Positive y will be up, and then toward the center will be positive x, which is a little unusual here on the page. It's to the left, but we typically make toward the center the positive direction, right? Because when you're moving in a circle, the centripetal acceleration is toward the center, so we call that positive. All right. So let's write the F equals ma equation. Okay, F equals ma in the x direction. Okay. In order to do this, I've got to put the free body diagram in here again for this car moving slowly. So let me pause and do that. Okay, you see an example of the free body diagram. I've already componentized the forces that don't line up with the coordinate axes, right? I broke them into right triangles that do. And then I also want to mark out on here, I want to mark out which angle is theta, right? Which angle corresponds to the bank angle of the track, right? The theta. So that's this angle here and then this angle down here. So when I go to write F equals ma in the x direction, you can see that the normal force and the friction force are opposed to each other, right? So that's going to look like this. It's going to be n sine theta, right? That's pointing toward the center, minus the friction force, and it's a static friction, right? Because the tires are not scraping along the track. Remember, we say that the tires are instantaneously at rest of the track when they're rolling without skidding. So it's the friction force, and that's going to be cosine theta, right? So it's those two forces in the x direction equals mv squared over r. Okay? So that's the way that the F equals ma equation looks like when the car is moving slowly, right? When friction is acting down the ramp. Okay? And then in the y direction, right, we've got n cosine theta, right? The ramp pushing up, plus friction's pushing up too as well, right? Sine theta there, minus the weight equals 0, right? That's what it looks like in the y direction. So put a y colon here, F equals ma. All right, let's go to the other side. Let's look at what it looks like when the car is moving at max speed, right, or close to max speed, very fast. Right? Remember, friction has changed its direction now, and in fact, I got this image from another source, and you can see here that the F equals ma equation has already been written. Okay, and you can see that the main difference, of course, is the change of sign. Right now, friction and normal force are working together to push the car toward the center of the track. All right, and then at the bottom, okay, the F equals ma equation for here is going to look, now friction is acting against it, right? So it's going to be all the same terms, but you have that sign change, S-I-G-N, that change right there. So that's a minus now, minus mg equals 0. In other words, the ground has to work harder now because friction is acting down the track, right? The track has to work harder. All right. The last thing about banked curves that I want to bring up to you is think about these two extremes here, right? If in one situation the car wants to slide down the track, and in the other situation the car essentially wants to slide up the track, doesn't that suggest that there's a sweet spot there somewhere in the middle as friction's switching directions where there's actually no friction? And that is exactly what happens. Okay, there is a situation like that. Let's go to the next screen. Okay, this is the no friction scenario. Right, no friction. It's that sweet spot right in the middle where the car is going sort of a medium speed, I guess, right? It's just about to start acting down the ramp. And in that situation, right, the only centripetal force would be the horizontal component of the normal force, right? So that's that sweet spot right in the middle. So sometimes you'll see questions like, you know, oh, at what speed does a car need to go so that I could drive on an icy track? Well, that's not really possible, right? Because the wheels wouldn't roll on an icy track. But the idea is that it can move in a circle without having any friction, right? The friction between the tires and the road would not be necessary for centripetal force purposes, although they would still be necessary for rolling purposes. So I want you to see the three different scenarios here, the two extremes, right? Friction when it's moving slowly, friction acting up the ramp, right, to keep it from moving down the ramp, and then when it's driving fast, right, friction's acting down the ramp to keep the car from sliding out, and then there's that sweet spot right in the middle where we have no friction at all. There you have it, banked curves.